Okay, thank you everybody for joining us. And I hope you are all having a wonderful holiday. So thank you so much for taking your time out to join us for this webinar meetup today. So thank you so much. So without taking much of our time, today we're going to be looking at structural equation modeling using Lavaan in R. So we're going to have the next 1-2 hours with our speakers. So going to go through the agenda for today. So we'll welcome all participants today. We're grateful you're here. Thank you so much. So we're also going to go a brief into the organizers of the Abuja R user group that will introduce our speaker. So then we'll give you the chance to...
She's in Abuja here. But then why is
Okay, sorry for that. Please, I'll employ everyone to kind of kindly mute yourselves for now. So when we're having the Q&A, we can allow others to speak as well. Thank you. So we'll let him talk. That's our speaker. Then we'll take the Q&A, maybe in between this the time that he's taking the floor and taking us through the topic of today. Then we'll be giving a vote of thanks at the end of the webinar. So now I will go briefly into introducing our speaker. So our speaker today is Adejumo Ridwan Suleiman. He is a data scientist currently working with Business Data Laboratory, and he also has other community input that he's doing, that supporting the community of data scientists also here in Abuja as well as in Kaduna as well. So please kindly mute. Okay. Okay. So, okay, thank you. So Ridwan is a data scientist with Business Data Laboratory, Abuja. So he has a strong background in mathematics, statistics, and computer science. Adejumo has extensive experience in developing and implementing data-driven solutions for a variety of industries. So in addition to his technical skills, Adejumo holds a degree in statistics from a reputable university here in Nigeria. So without taking much of our time, I'm going to call in Ridwan to give the talk for today. Ridwan, are you there? Hello, Ridwan.
And I'm also a statistician at the Federal Teaching Hospital Gombe, and I'm also a Udemy instructor. So today I'm going to be talking about structural equation modeling. And I know SCM, though it might be a new term for some people, for some of you listening, but I know some of you are already familiar with the concept of what SCM. So what are we going to be looking at throughout today's session? First of all, I'm going to be introducing the concept of SCM. I'm also going to be talking about the key concepts in SCM, and I'm going to be giving an overview of the Lavaan package and also model interpretation in SCM analysis. And also I'm going to be conducting a case study. Then I will give a summary of what I've already discussed so far, and then a Q&A session. So now, introduction to SCM. So SCM is actually a multivariate statistical analysis for describing relationship between latent and observed variables. So this is the main objective that SCM is trying to achieve, describing relationship between latent and observed variables. And when we talk about latent variables, we are talking about variables that one can't actually observe. So unlike our regular statistical analysis where we collect our data from what you have actually observed, for example, now something like weight, height, let's say in a study where in a particular study where someone has conducted a study, or maybe patients in a in a particular hospital. So you collect the weight of these patients, the height of these patients. So these are like variables which you actually observe, to actually get from the patient. But there's some variables that at times are not observable. So these are what we now call latent variables. So it is structural equation modeling that allows one to be able to create relationship or describe relationship between these latent and also observed variables. And it is also a multivariate statistical analysis, which means that it is used when we have more than 2 variables. So it's the extension of multiple regression analysis and factor analysis. So it tends to solve the problem which multiple regression analysis and factor analysis can't. So regression analysis is actually where we have more than 1 variable or a single variable predicting another variable. So for example, now I want to predict the score of a particular student based on the score, based on his previous score, maybe in the last session or last semester. This is an example of a multiple regression analysis. While factor analysis is a situation whereby we have variables that are related to each other, or let's say connected to each other. And we know that sometimes in statistical analysis, variables connected to each other, we have what we call multicollinearity, where variables connected to each other actually will not give us a good model fit. So factor analysis combines these variables into one single variable. So a typical example is when a study you have 2 predictor variables such as a BMI, and you also have weight. So we know that weight is actually in calculating BMI. So by virtue of actually performing correlation analysis on these 2 variables, you see that they're correlated to each other. So instead of using both of them, you can actually combine, let's say, 2 of them into one, or just take one of them out of it. So this is what factor analysis is all about. So SCM tends to extend these 2 techniques, multi-regression analysis and factor analysis, which means you can implement these 2 techniques actually inside SCM modeling. That's structural equation modeling. And also it is mostly used a lot in social sciences to test theoretical constructs. So I already explained earlier on about latent variables, so such as attitude and beliefs. So I don't think there's a way you can actually measure an individual attitude. Let's say, okay, you can know an individual attitude is 1, or individual attitude is 2, or an individual attitude is 0.5, something like that. So this is where SCM actually comes to play, because these are theoretical constructs. So what they actually do is that they find observed variables which are actually linked to this. They find, okay. Somebody's so okay, I'll try and reduce my speech. Okay, sorry for that. Okay, so what was I? Okay, I say in social sciences, they actually use structural equation modeling to test theoretical constructs. So these theoretical constructs are usually sometimes attitudes, beliefs, and values. So what they do is that we measure these items through multiple observed variables. Since we know that there is no way of measuring these variables, and in reality, we don't have no way of measuring these variables, unlike other variables such as an individual's height, an individual's income, something we can actually get from the individual. But when you look at an individual, you cannot just say, okay, this is where I'm going to measure the individual attitude, or this is the way I'm going to measure this particular individual's belief or this individual's values. So how do you now take care of such problem when you now know that you want to analyze what, or you need that such variable inside your analysis? So this is where you now use your SCM to create relationship between these latent variables and your observed variables. So this is your theoretical construct, such as attitude. For example, now instead of attitude, you can find variables which you can actually measure, such as, let's say, income. Now you can actually say, okay, we know that these are individuals' income. I can actually use this income, and also you can pick another variable to now link them as the observed variables to that particular latent variable, such as what, attitude. So this is where social science usually tend to use SCM analysis to analyze these theoretical constructs. So it's also used in psychology, where latent variables such as personality traits or intelligence, just as I explained earlier on, unobserved variables, things that I cannot observe, are measured through questionnaire. So we have questions that will now link them to a particular variable. From these questions that we can now create that particular latent variable and use it inside the analysis. So what are the benefits of using structural equation modeling? Is used to model complex relationships with integrated variables. So most of the times, some of these complex relationships can't be modeled using other statistical techniques. So you have to use SCM analysis. When your model tends to get complex, SCM analysis usually used to be the best technique to use to model complex relationship and integrated variables, and also provide estimates for direct and indirect effects. So a situation will come by where you have a variable affecting another variable directly or indirectly through another variable. So you tend to use SCM analysis to solve such problem. and also have the ability to handle missing data and provide parameter estimates in the presence of missing data. So one of the advantages of using SEM is that when you have missing data, so unlike maybe regression analysis or logistic regression, which tend to be affected by missing data, whereby you have to find a way which are going to take care of this missing data, either by removing the missing data or you use the mean to replace those particular missing data. So in SEM analysis, regardless of you having missing data, you are still likely to get a good parameter estimate and also a good model fit. So these are some of the problems that the benefits of using SEM analysis. So it also has its own limitations, just like other techniques also in statistics. So one of the limitations of SEM is that large sample size to obtain reliable estimates of model parameters. So SEM need a very large sample size. Some statistical techniques might not actually need large sample size. Some maybe, for example, 100 is okay, 200 is okay. But in terms of SEM, we need a very large sample size to get a reliable parameter estimate. So we're talking of a very large sample size, and some other times getting a large sample size is very costly, depending on the survey which one is trying to perform. So this is one of the limitations of structural equation modeling. It also requires a well-specified theoretical model, because most of the times when you want to conduct an SEM analysis, you're going to be the one specifying your model, just like what I explained earlier on, just from previous surveys or previous literature, which one I've already investigated on. Well, one is explaining how large. So though this depends on the study which one has already read on. So if one wants to conduct SEM analysis, so based on the previous study which I've already seen or maybe already conducted, it depends on how you're going to get some sample size let me just put it like this. Some sample size might be large for one study or might be small for one particular study, and it will be sufficient for another study. So it depends on what you're actually surveying on. Okay, another thing also with SEM analysis is that it is difficult to learn. So these times when you go to the mathematical aspect or how the model was actually built mathematically, so it is difficult to learn in terms of the mathematical aspect, and also sometimes in terms of you implementing it. And also familiarity of statistical softwares and advanced statistical concepts is also needed, because sometimes this analysis tends to combine a lot of statistical techniques together, such as regression. You have it in SEM analysis, covariance, you have it in SEM analysis, correlation, you have all of this inside SEM analysis. So it tends to combine a lot of these statistical concepts, which sometimes some people are not familiar with. So application of SEM is actually applied in a lot of fields. These are just some of the fields which SEM is applied, such as in psychology. I already explained earlier on how we apply SEM in psychology, where you want to find out about attitude, belief of an individual, let's conduct study on top of the attitude of an individual. Also have in social sciences, social support. These are things that we can actually observe. So we need to use SEM analysis to be able to analyze such properties or traits. Also having education, students' performance, teachers' performance, students' scope. These are kind of things that are not actually directly, they're not achievable by a single variable. We need observed variables to be able to solve such problems. And we also have in business, we want to see our customer satisfaction, or we want to see our performance. These are places also we can use SEM analysis to also solve such an issue. So these are just some of the few places which you apply SEM analysis. We also apply it also in health. So a lot of fields SEM analysis actually applied on. So we have the key concepts in SEM. So the most important key concept in SEM is actually the issue of the latent and observed variables. So the latent variables, first of all, the observed variables are measured directly. So these are variables which one actually measured directly. A typical example now, already explained earlier on, is the height, the weight of an individual's variables that we can actually get information from. And latent variables are not directly measured and are inferred from observed variables. So which means information based on the latent variables are actually gotten from observed variables. So when you want to conduct an SEM analysis, you already have your latent variable, which you want to conduct analysis on. So it's not left for you to now see which observed variables is this particular latent variable actually influencing, that can give you information regarding this latent variable. So which means that when you are constructing your model, you need to make sure that the latent variables you are using and the observed variables you are using actually have a relationship with each other. You might be using more than one latent variable, you might be using two latent variables, and sometimes you might have a situation whereby the two latent variables are actually predicting another latent variable. So that's why I said earlier on that it's actually used for solving complex relationship. So when you already have observed variables influenced by particular latent variables, and two or more latent variables can actually be predicting another latent variable. And these latent variables are also known as latent constructs. We also call them latent constructs. So now this is the typical example now you can look at. So let's say in a study where in a study where I'm having happiness as a latent variable, you can see happiness, and I'm having income and marital status as my observed variable. So you can see that income is actually an information we can get from an individual. And an individual might be earning, let's say, 1 million per year. We can use monthly, let's say 200,000 per month. So this is an information which can actually get from that particular individual. And we have marital status. Is the person happy? This can be marital status. It can also be relationship status. Is the person in a relationship or not, or is the person married or not? So just basically, we're just making an assumption based on maybe other studies we have already seen. We want to know that, okay, how does happiness actually what's caused it? Because happiness currently is the latent variable. So you can now see that the arrows is pointing from happiness to income and how happiness to marital status, because this happiness is what is actually influencing this variable. So one will ask that, why is that the arrow is not going from income to happiness or marital status to happiness? So one thing we need to notice is that the latent variable is actually influencing the observed variables, in the sense that if not for the latent variable, we might not be having these observed variables here. So imagine we have another latent variable now called anxiety. So we might not be using these particular observed variables. So that is why you see these arrows are pointing downwards to these particular observed variables. So to give us information based on that latent variable.
Hello, please.
So next is path diagram and notations. So the graphical representation of relationships.
Yes, it's okay now.
Yes.
Your screen is appearing, but please go easy with us. It's as if you are playing your sound from an audio. You are too fast, sir.
So is my screen appearing?
Yes, sir.
Yes. You can see your screen now.
Okay. Take that as a yes. Everybody is seeing my screen. Okay. So still on the path diagrams and notations. So this is our path diagram, which I already showed earlier on, I was explaining the latent variables and also the observed variables. And I already said that the path diagrams, the observed variables are usually represented in squares or rectangles, while the latent variables are represented in oval shape or in circular formats. So depending on what your choice is. And this is also how it's going to appear regarding the software you're going to be using to analyze to perform your SEM analysis. And you can see the arrows, they always point down from the latent variables to the observed variables. So the next is endogenous and exogenous variables. So endogenous variables are variables that are hypothesized to be caused by other variables in the model, while exogenous variables are not influenced by other variables in the model. So the difference between these two is that endogenous variables are actually influenced by other variables in the model. So they actually have arrows pointing to them inside a particular model, while exogenous variables don't have arrows pointing to them. So they actually point the arrows into other variables. And in the path diagram, one thing we need to know is that latent variables can actually be endogenous or exogenous. Same thing with also observed variables, depending on the model which one is specifying. So any of them can actually be endogenous or exogenous. It depends on the variable, which the variable, is it pointing arrow to another variable? That is it causing another variable, or this variable is being influenced by another variable. So it is the difference between the endogenous and the exogenous variables. So you can see now inside this particular diagram, now you can see our latent variable now, happiness. In this example now, it is the exogenous variable because it is pointing into two variables, which is income and marital status. And this income and marital status are the endogenous variables because they have happiness. They are actually being influenced by the latent variable happiness. We can also have a situation whereby this happiness can actually be also pointing arrow into another latent variable. So let's say, for example, now we have another latent variable now called, we can just give something as anxiety. So now this particular anxiety now in this situation will become an endogenous variable, while this also still remains an exogenous variable. So we also have what we call direct and indirect effects. A direct effect is direct relationship between two variables, So when you have a direct relationship between one variable to another variable, so based on our example earlier on, we have relationship between happiness to marital status. So this is a direct relationship. Why an indirect relationship? We actually have another variable in between. So we call this variable the mediator. So an indirect refers to relationship that is mediated by one or more variables in the model. So if we have another variable in between, we call that variable the mediator. So instead of, for example, happiness to be influencing income, we have another variable that's going to be coming in between. Just like you are looking at now in the diagram, you can see that the direct effect by this side, we have happiness influencing marital status, and we also have happiness influencing occupation, but being mediated by what? Income. So this is an example of an indirect effect. In this situation now, we know that, okay, even though happiness is actually having a relationship with occupation, there's actually a mediator in between called income, why happiness also have a direct effect with income. So before I go on to the Lavaan overview, is there any questions? Is there any questions so that I'll answer them?
Yes.
Okay, go ahead with your question then.
Yes, apart from the use of software, what are the theoretical ways of solving this, your SEM? And in your application that
are there any questions before I can continue?
You didn't make mention of something like econometrics. When we talk of the simultaneous equations of which there are structural equation models.
It's like he's not hearing you at all.
It's not hearing me.
Okay, I think I'll move on.
Oh, you hear
Can you hear me?
He can't hear you. Yeah.
So you can go ahead with your question now.
Yes, actually, what I was trying to ask is this. Apart from the use of this Lavaan package, what are some of the methods? Maybe you are using pen and paper to solve this SEM. Because when you talk about that, you didn't talk about the reduced method of how to solve it. Is it that there's no manual way of computing the SEM? Thank you very much, Mr. Ridwan.
Okay, well, I like your question. So that's why I said earlier on, one of the limitations of SEM is that is actually difficult to learn, because the mathematical way of actually solving SEM is very, how will I put it? It's a multivariate.
It's complex.
Ratio of matrices and things like that. So I not actually include this in this presentation. So I'm just talking about how you can just apply your Lavaan in R, and also I can also use it to perform SEM, because there's even no way safe you are going to be using a manual way to actually solve for SEM. Those are actually, but if you want to find out about the manual way, I think, I don't know, inside the references I'll be given at the end of presentation, I think I gave a link to a particular article. I think you should be able to see the mathematical formulas of the using SEM analysis. So I think, does that answer your question?
Yes, go on. Actually, I normally solve it with, and I'm a statistician, and at the same time a lecturer. I've done this for my students before. That's the reason I was asking. Thank you very much. Continue, no problem.
Okay. Hello, sir. Can I also ask you my question?
Okay.
Yeah, go ahead.
Yeah. With the diagram you showed us, my name is Asari, where there is a relation between happiness, income, and marital status. Is it a real life theoretical model, or it's just something hypothetical? I'm saying this because I'm thinking that one's income and one's marital status would cause one to be happy, not the other way around. Thank you very much.
Okay, I think you're getting it wrong here. So I want you to look at it in such a way that, I think, let me go back to the diagram. Okay, so this is the diagram. So actually explaining latent variables and observed variables. So why I'm even using this example, because I've already conducted a study before based on this particular example using the World Happiness Report, where there was actually information on GDP, and I think there was also actually another info, actually forgetting the other variable which I actually used. But if you look at it, I'm talking about relation between latent and observed variables. So based on this three now, which one can you actually get information from an individual? I'm very sure you can get information of income from an individual. So you can actually get the details of the person's income. I can also get details of the person's marital status. But I don't know, maybe a particular index that is used So sometimes some indexes are used to determine one's happiness. Most of the times, we know that happiness is actually something that I cannot observe directly from an individual. Even if an individual tells you that he's happy, it might not actually be happy. But based on these observed variables, or maybe from previous studies, which you know from these observed variables, you can know that, okay, income and the marital status are actually observed variables, which, how will I put it, the happiness actually was influencing.
Sorry, sir. I think what he's saying is about the affectation that happiness predicting income and marital status, just like you earlier said. He was thinking that the other way around should be the case, that income and marital status should be the ones to predict happiness. I think if I get him right.
Okay, so, please, I don't want to be using the term predicting. We are not predicting anything in this place yet. It's a relationship between latent and observed variables. There is no prediction going on in this place. We're actually relating between happiness, income, and marital status based on latent variables and observed variables. So we are not predicting anything yet in this place. So even if we are to specify this model inside Lavaan in R, we are not going to be using the tilde sign, which is used to predict independent variables or dependent variables. We're going to be using the tilde and equals to sign, which I'm going to get into earlier on. So we're not predicting anything yet. I'm not going to anything predicting. We're actually relating between happiness, income, and marital status based on latent variables and also observed variables.
So with that being said, then let me say, are the arrows not confusing? Because if you use that direct arrow from happiness to income and happiness to marital status, isn't it interpreting that happiness in one way or the other is kind of making someone's income either go high or low, and then one's happiness is making one's marital status either.
That is why I was saying that we're not actually predicting. So let me explain the issue of the arrows. So the reason why you see the arrow is pointing from the latent variable is because the latent variable is actually what is causing these observed variables. Because I actually explained earlier on that why these arrows are pointing downwards and not upwards is because imagine we're using anxiety. Now, we will not be having these variables inside this place, which means because of this happiness, that is why we're having these particular variables in this place. So that's why I say if you are trying to bring in prediction, you might get it mixed up. So you just take it as this particular happiness being causing this income and also the marital status. And also when you get your path diagram inside any software that you're using, be it R or maybe Amos, this is how we are going to see the diagram appearing to you. Latent variables always have the arrows pointed to the observed variables. Whether the observed variables is 1, it is 2, or it's more than that, the arrows always point from the latent variable to the observed variables. I'm going to show later on an example of a path diagram generated using R, and you see how it also looks like the oval shape actually have the arrows pointing to the observed variables. And also inside that particular diagram I will show you later on, you also see an example of how the regression is also represented inside the path diagram.
Okay, right. Thank you very much.
You're welcome. I think, is that all the questions?
So far, I think.
Yeah, we'll continue from this spot and then we'll continue with the questions later. So you can go ahead.
Okay, so the next now we're going to be talking about is an overview of the Lavaan package. So this is the Lavaan package, actually stands for latent variable analysis, as an R package that is used for structural equation modeling. So we have other softwares for SCM analysis, but this is this package that allows us to be able to perform SCM analysis inside R. So first of all, we need to install the package. We're using the install.packages function and also load the package using the library function. Then the next is also creating a model object. This is very important when one is doing SCM analysis. This is where I'm going to specify the relationships between your variables. So this is an example of a very simple model object. You can see that we have two observed variables. We have two variables here, x1 and x2, and we also have another third variable called y. So from this now, we can see that x1 and x2 are having a relationship with the latent variable y. So what makes this a latent variable relationship is because of this particular sign, the equals to sign and the tilde sign. So the equals to sign and the tilde sign signifies that, okay, these two variables are actually observed variables that are being caused by this particular latent variable. So why this particular tilde sign alone, which most of us are already used to or we know about, specify regression between outcome and predictor variables. So in terms, when your model gets complicated, you can also signify where some latent variables are also predicting another latent variable using this particular sign. Then we also have the double theta, which specifies covariance between variables. These are variables which are actually, I will not put it, well, let's say they actually covariate with each other. They are actually covariates of each other. You specify them using this particular sign when creating your model object. So after I'm creating your model object, you use the SCM function with your model as an argument and also your data as an argument. So in this question, in this example, now you can see that my data is actually my data. So I'm giving only two arguments. First of all, the model object I created earlier on, and also the data which I am using. And after fitting this particular model, you're going to get the summary statistics from this particular results using the summary function. And also give the argument standardized is equals to true. Why we're giving standardized is equal to true is that because we want to standardize the coefficients on the variables, whereby some of them are not measured on the same scale. So by making standardized is equal to true, we actually have the coefficients, we can actually relate to the coefficients with each other and also get the most, how will I put it, the coefficient that actually, the variable actually relating most with what you're actually measuring. So we're using standardized is equal to true, we are standardizing the coefficients that we're having inside our model. So next is the model interpretation. How do we interpret the model that we have from a latent variable analysis? Our parameter estimates and standard errors. So our parameter estimates are values of the coefficient calculated for each predictor variable in the model. So each predictor variable is actually going to have a parameter estimates, and these are the coefficients actually calculated for each predictor variable. So it allows us to know how the a particular predictor affects a particular outcome variable. So let's say the higher the coefficients, you know, then the higher how that particular predictor affects that predictor variable, that outcome variable. I mean, we also have our standard errors. These are ways of measuring the uncertainty in the estimation of these coefficients. So a lower standard error means that that particular coefficient is more likely to be relied upon than a higher standard error. So whereby we're having a standard error, we know that we have a high measure of uncertainty in that particular coefficient. So we have the fit indices, which are actually used to measure the goodness of fit of our SCM model. So the first fit indices is the chi-square. We also have the root mean square error approximation, RMSCA, and we also have the comparative fit index, CFI. We also have the Tucker-Lewis index, TLI, and we have the standardized root mean square residual, SRMR. So these are fit indices that are actually used. So most of the times, though some study actually are okay with just one of these fit indices being met, while others are okay with maybe 2 or 3 or more being met. So most of the times when perform an SM analysis, it's not necessary for you to actually meet all the requirements for these fit indices. So these fit indices actually have benchmark values. And what I mean by benchmark values are the values that allows you to be able to know that this particular model or SCM model you have already conducted is a good fit. So a non-significant chi-square value actually indicates a good fit. So which means that your chi-square value is actually, the p-value of your chi-square is greater than 0.05, depending on the significance level you're actually using. But it also has a disadvantage. One thing with the chi-square is that the situation where you have a large sample size, then it's always going to be returning a non-significant value, regardless of how good the model fit is. So even if your model fit is not good, it's still going to be returning a non-significant chi-square value for you. So which means this particular fit index cannot be relied upon. So in the situation whereby your model is not actually poor, but you have a very large sample size, the chi-square value actually return a non-significant value for you, and you're going to be thinking that your model is actually a good fit. So most of the times we don't actually use the chi-square value, but we also have the RMSCA value, which is the root mean square error approximation. So the root mean square error approximation, a value of 0.05 or less is considered a good fit. So a situation whereby you have a value of 0.05 or less, then you know that this particular model that you have is a good fit. And also where you have a value between 0.05 and 0.08, it also indicates a reasonable fit. But where you're having values above 0.1, then you know that you have a poor model fit. Then the next is comparative fit index. So comparative fit index, a value of 0.9 or above indicates a good fit. while a value of 0.95 indicates an excellent fit. So which means that when you are performing such analysis, when you are actually looking at your CFI value, any value you're having less than 0.9, you know that you're actually having a poor model fit. Not to talk of even having values that are actually below 0.5. So if I have the Tucker-Lewis index, a value 0.9 or above indicates a good fit, while a value above 0.95 indicates an excellent fit. So this is just similar. The benchmark is also similar to that of the CFI, as I explained earlier on. I also have the SRMR value, which is a value of 0.08 or less is considered a good fit, while a value between 0.08 and 0.1 indicates a reasonable fit. Values above 0.1 are considered a poor fit. So when you have a value above 0.1, you know that your model is poor. But any value that is less than that, you are good to go with your model. So just as I said earlier on, it's not necessarily when you perform the analysis, you meet all these conditions. At times, in some studies, when you look at it, some of them are just okay with this. They actually lay more emphasis on some of these CFI and the TLI values. And sometimes also when I also perform the analysis, to actually meet all these conditions. But most of the times, the chi-square, because of sample size, as is affected by large sample size, indicating that it's a good fit regardless of situation where it might not be. So it's not actually a fit index that's to be relied upon. So before I go for the case study, is there any questions regarding what I already spoke about?
I have a question, please.
Okay.
Thank you so much for this wonderful presentation that you are giving us. Okay. My question is regarding the observed variables.
Okay.
Is there a kind of or does the level of measurement of a variable influence its its ability to serve as a good observed variable? Are there any kind of limits to what kind of level of measurement that you use? Let's say nominal versus interval and all that. Thank you.
Okay. So one thing I forgot to have noted with SEM analysis, you actually use SEM analysis, either you're having a nominal value or you're having a, let's say, continuous variable. So you can actually, your observed variables can be any of these forms. Most of the times from previous studies, you see most of the time they actually use it to have continuous variable. But because I already explained earlier on, it's actually in psychology questionnaires. I know most of the times questionnaires are usually in a nominal variable or categorical variable. So it's actually, you can actually use your observed variables either in terms of nominal variable or in terms of continuous variable. But most of the times you get good results when you use the observed variables. Actually, they come in the form of continuous variables, like the case study we're going to be going into now.
Okay, thank you very much.
So this is the case study I'm going to be studying.
Sorry, sir. Okay. Does that mean that any form of the variable is accepted?
Yes, any form of the variable is accepted. Any form.
But especially if it is a nominal form of variable.
Yes, I already said around that those in psychology use it in questionnaires, and questionnaires come as categorical variables, or at times they even come as nominal variables. They come as nominal or ordinal variables. So.
Yes, actually, I had Likert scales in mind when I asked this question.
Yeah, that falls under nominal, the ordinal variable, the Likert scale.
Ordinal, categorical. Yes.
You can also use that. Can I go on?
I think you can go on now. Thank you.
So the next is a case study which we are going to be conducting. So this particular case study is actually a data set that comes with the Lavaan package. It's the political democracy data set. So the data set contains various measures of political democracy and industrialization in developing countries. So first of all, we have our latent variable political democracy in 1960. So you can see why it's called a latent variable. Imagine political democracy in Nigeria in 2015. So how do you have such information? Where can you get a data that's measuring that? So you can see that political democracy in 1960 is regarded as a latent variable. Then we now have the observed variable we have that we know that these observed variables can give us information of these particular latent variables, which is political democracy in 1960. So we have expert ratings of the freedom of the press in 1960. So we have these are ratings. So this is continuous variables which we actually have. Then we have the freedom of political opposition in 1960, which is Y2. Then we also have Y3, the fairness of election in 1960. So these are actually the actually observed variables, which means we have values regarding this. Then we also have Y4, the effectiveness of the elected legislature in 1960. So these are the 4 observed variables which we are going to be using to, which we are going to be relating with our latent variable, political democracy in 1960. Then the next that we have is political democracy in 1965. So this also has its own observed variables, expert ratings of the freedom of the press in 1965. Then we also have Y6, the freedom of the political opposition in 1965. Then also have Y7, the fairness of the election in 1965. Then also have Y8, the effectiveness of the elected legislature in 1965. Then that is for our second latent variable. Then for our last latent variable is the level of industrialization in 1960. Then also have the observed variables under it, the GNP per capita in 1960. This is the gross national product. We also have the X2, the inanimate energy consumption per capita in 1960. They also have X3, the percentage of the labor force in industry in 1960. So you can see these are the latent variables that we have. So now you can now see the hypothesized relationship between these variables now. But this is the diagram that's actually outputted by the Lavaan package. So you can see our level of democracy in 1960 represented as a circular shape. I can see the level of democracy in 1965 also represented in circular shape, indicating that these are latent variables. And you can now see also these arrows pointing at these particular observed variables, Y1, Y2, Y3, and Y4. So this is for the level of industrialization, level of democracy in 1960. You can also see the that of the level of democracy in 1965. You can see that the observed variables here are Y5, Y6, Y7, and Y8. They also have our level of industrialization in level of industrialization in 1960. You can also see the observed variables here, X1, we have X2, and so on X3. Why these arrows indicate the covariance? So which means any arrow, you can see that this arrow are actually double-ended, which means that what? These two variables are covariant of each other. Same thing you can also see in this place, Y2 and Y4. You can also see Y3 and Y7. So most of the times, this particular diagram is to be plotted manually, maybe by your hand, or maybe from previous studies. See, someone have already done it. You want to also apply it on another data set. So we are going to just draw this diagram, just say manually, to see how these particular variables are related to each other, because you are going to be using this information when you are specifying your model object, just as you see next. So you can see that level of industrialization have an arrow pointed to level of democracy in 1960. And also have an arrow pointed to level of democracy in 1965. So what this means is that level of industrialization is actually predicting level of democracy in 1960. While level of democracy in 1960 and level of industrialization in 1960 is predicting what? Level of democracy in 1965. So this particular, what they're actually trying to do in this study is that their main aim was even actually to predict level of democracy and level of industrialization in 1960, not to predict level of democracy in 1965. But because they don't have such information, I'll let explain earlier on as a latent variable, that was why they had to use these observed variables to get information regarding this. Anything they have regarding this particular latent variables, they will now use it to predict level of democracy in 1965. Okay. So now let me go to my R to show us. So this is now our case study, which we are actually trying to analyze. So you can see that this is what we use to install the package, the Lavaan package. And you can also see we have already loaded our library, Lavaan, at line 5. Now let me have a view of this particular political democracy. So let me load this library. So you can see the political democracy data sets. So you can see the information we are having regarding each particular observed variables. You can see currently now we're having what continuous variables all through. But in some situations where maybe you're using a questionnaire, you might be having categorical variables. So you can see that we're having continuous variables all through. So these are all the observed variables that we are dealing with in this particular analysis. So now this is the model specification. So first of all, we're going to be giving our measurements model. So you can see this is our measurements model where we are specifying the observed variables to the latent variables. So you can see our X1, X2, and X3 are our observed variables. And you can see that we have specified them to the level of industrialization in 1960. Same thing also applies to this particular line. We have Y1 to Y4, which have been specified as the observed variables of level of democracy in 1960. Then we also have Y5 to Y8, which are specified as the level of, which are specified as the observed variables of level of democracy in 1965. And after that, also in this particular model object, we specify our regressions. So you can see our regressions now. Level of democracy in level of industrialization in 1960 is predicting level of democracy in 1960. And you can also see that level of industrialization in 1960 and level of democracy in 1960 is predicting the level of democracy in 1965. So this is our regressions. And this is actually what we want to even achieve. But we just have to get information regarding these latent variables so that we can now predict it. We can now use these latent variables to predict what we're actually interested in. Then we have our residual correlations. These are variables that we know that covariates of each other. So let's just put it in the layman term as variables having relationships with each other. You can see Y1 is a covariate of Y5. Why this one signifies that these three are covariates of each other. Y2 is a covariate of Y4 and Y6. So even if you interchange it, Y5 to be covariate of Y1 is still the same thing. So when you see a situation where Y4 plus Y6 or plus another variable, we know that all these variables are covariates of each other. Then we also have Y3, which is a covariate of Y7. We have Y4, which is a covariate of Y8, and also Y6, which is also a covariate of Y8. So this is the measurement model which I've specified. And this is in line with that particular diagram which I showed earlier on. So now if we want to create this particular object, we're going to highlight all and we run it. So I already created our model object. So the next is now to create our model fit using the SCM function. So the only thing we just have to give now is just to give our model objects and also give our political democracy data sets. So by doing that now, we're just going to use the SCM function and create our model fit. Next now is also to get our summary statistics regarding this particular SCM model we have. So now I'm going to be giving our fits. These are model fits, and we also set fit measures to true. So these fit measures are measures which measure, these are the model indices I explained earlier on that measure our model fits. They also have standardized intervals to true. Just also like I explained earlier on, I'm also going to be running this. So you can see the results from our summary statistics of what we are having. So let me expand it. Okay. So you can see the results we are having. So first of all, now this is the chi-square 0.329. You can see that the chi-square signifies that it is not significant. So which means we have a good model fit. But I already explained that we cannot be relying on the chi-square because of if our sample size is actually large. Then you can also see our CFI. Our CFI is 0.995. They also have our TLI, total Lewis index, is 0.993, which indicates our model is a very good fit. Also, you can see the value of our RMSCA, which is 0.035, which is not as high because earlier on I said if RSCM is greater than 0.1, then having a 4 model fit. You can also see the confidence interval for the RMSCA value. We also have our standardized root mean square residual, which is given as 0.044. You can see our SRMR value is given as 0.044, which also indicates that our model is a good fit. Also, we also have our latent variable estimates. You can see most of the estimates of these particular observed variables. You can see the estimate that we're having. And I also have the results of our regressions. You can see the estimates for our regression, and you interpret this just like you interpret your regular regression analysis. So now these are our level of industrialization in 1960 and level of democracy in 1960. So which means that a unit change in the unit change is a level of industrialization in 1960 is going to affect level of democracy by 1.483. So this is just what it means. I can also see our p-value, which indicates that these particular predictors are actually what? They are all significant. But the level of industrialization in 1960 in predicting level of democracy in 1960, and also the level of industrialization in 1960 and level of democracy in 1960 in predicting level of democracy in 1965. You can see that all the p-values are significant, which means that all these predictors are actually significant in predicting level of democracy in 1965. You can also see the value, the estimate of our level of industrialization in 1960, which you can interpret as a unit change. A unit change in the level of industrialization in 1960 is going to affect the level of democracy in 1965 by 0.572. And you also have a unit change in the level of democracy in 1960. It's also going to affect the level of democracy in 1965 by 0.837. So this is actually what we're actually interested in all this analysis. But we actually need those observed variables because there's no way we can actually measure this or we can get information regarding this. So this is one of the main aims of structural equation modeling. And also at the end, you have the covariances. You can also see our covariances, the estimates, and you can also see our p-values. But these are most of the information we actually need most, actually the fit indices and also the regression coefficients, and also the significance of these regression coefficients. So next also now is also our Lavaan plots. So just to plot the diagram we have earlier on, the diagram I showed earlier on was actually plotted by another package, which I think is called SemPlot. But this one is actually, this one I'm going to be plotting now we are going to be using the Lavaan plot. So most of the times, the Lavaan plot gives a more nicer plot than the SemPlot. So this is the Lavaan plot. It's also another library on its own for plotting your SCM model. So I'm going to run it and also run the Lavaan plots. So we give the model as an argument and also coefficients as true. So you're not going to be seeing most of these observed variables coefficients. So which we also call as factor loadings. We also call most of these coefficients between observed variables and latent variables. We regard them as factor loadings. Are you seeing this diagram I'm showing? I've zoomed it. Is it appearing?
Yes, it's appearing. We're seeing.
Okay. So you can see how it looks like. So it's just similar to what we had earlier on. You can see the arrows, level of industrialization in 1960, predicting level of democracy in 1960. You can see the coefficients here, 1.48. You can also see this in 1965. You can see the coefficients here, 0.57. And you can also see that of level of democracy in 1960, predicting level of democracy in 1965. You can see also the coefficient 0.84. And these are also our factor loadings. So most of the times in some literatures, they say the factor loadings less than 0.5 needs to be dropped because it's not contributing anything to that particular latent variable. But if you look at it here, you can go see that most of our factor loadings are actually above 0.5.
Okay, we can't. Okay, good.
Okay, so this that is the end for our presentation based on structural equation modeling. So, but there are more to it. That is why I provided some resources at the end of this slide. But first of all, before I share the resources, I'm just going to give a summary of what I've been explaining earlier on. So we know that our key takeaways is that structural equation modeling is actually used to analyze the relationship between latent and observed variables. This is the main thing in SCM analysis, latent and observed variables. Whereby we have observed variables all through, I don't think there's any need to be using SCM analysis since we already have tools like regression analysis. But when we have one particular latent variable, and we also want to use that latent variables to predict another latent variables, then this is one of the problems which we want to solve using structural equation modeling. And also we know that the Lavaan is also an R package for SCM analysis, which I also feel is even easier than other tools such as AMOS that is usually used in SPSS for performing SCM analysis. And also we have the libraries which we also use to plot our SCM diagram. Either you're using Lavaan plot or you want to use SemPlot. So, and also when using Lavaan, I explained that it's important to specify the model because specifying your model matters a lot Because at times you might have the right variables, but you may specify the model. And what I mean by specifying the model is that, like that our example earlier on, let's say Y1 was actually an observed variable for the latent variables level of industrialization 1960. We now can use that particular observed variables for another latent variable. So this is going to give us a poor model fit. And also, if you use few number of observed variables for particular latent variables, let's say a lot of information is not covered for that particular latent variable, we're also going to get a poor model fit. So this is all part of specifying a right relationship between the variables and also constructing a good measurements model for the latent variables. And also we're able to test our model fitness using the various indices I talked about, the chi-square, the RMSU, the CFI, and also the CLI. And also when interpreting the results, it's important to consider both the statistical significance of the estimate and also their practical significance. So when we mean by practical significance in real life, how this particular variable is actually affecting this variable in real life, and also in our analysis, is it significant? Is the variable actually significant? Be it the factor loadings, they also have their p-values, and also the regression estimates or the regression coefficients, they also have their p-values. And also, finally, SCM is actually a powerful tool that helps researchers better understand complex relationship between variables, because it's actually important to be used appropriately and also with caution. So these are some of the resources which I'm going to be sharing. So the first resource is chapter 6, structural equation modeling, introduction for data science. So I don't know, maybe I have a preview of the link.
Okay.
Okay. So I think we'll just be sharing the link later on.
Okay. Thank you so much. Okay, I can see the links are coming up now. Okay, we have some questions. Sorry, can you hear me?
Yeah, I'm hearing.
Okay, please, before we go into the resources, we have some questions, and Victor is raising up his hands. So maybe you'll use this time to take the questions before we round up.
Yes, we also have some questions.
Okay, please, let's take it one by one. Victor, can you go ahead while I read out the question in the chat box afterwards?
Okay, thank you very much. Thank you, sir. Thank you, sir, for this great, insightful presentation. I really learned a lot today.
Thank you.
I have two questions. The first one is R related. I noticed when you were the syntax you used to write the model, you used a string to capture the variables as well as the operators.
Okay. Yeah.
So yes. So I thought that was very, very intriguing to me. My question is that this thing you did, is it unique to the Lavaan package, or is this something that is doable in R in general?
No. It's only from the Lavaan package. That model object is actually a string.
Yes, it's a string. Yes. So that was what I observed. Okay. All right. Okay. Then my second question is between the latent and observed variables. Do we have anything like one-to-many, one-to-one, or many-to-one relationships, whereby in the example you gave us, we have many observed variables, okay, referring to or indicating a latent variable.
Yes.
Do we have a situation where one variable is observed, but it will give us some other latent variable as an maybe be somehow interpretive in function, or do we also have where many variables, observed variables, could one observed variable could be related to different latent variables? Do we have such instances?
Yes, it's possible, sir, because it depends on your study and what you have also, because that's why it's important when conducting such analysis, you look at other studies, you go in depth, even though most of them are not using the data similar to you, you look at what you have, because that's one very important thing in SM analysis. The model specification is very important, because you as the researcher, you're not actually specifying these models. So you need to know that, okay, this particular observed variables is actually related to two latent variables, because it's possible a single observed variable might be related to two latent variables. And it's also possible that we have also one latent variable to two observed variables. So all those kind of situations are possible. So it is when you're actually typing your model, you're actually specifying your model, you're going to be typing those. So when you actually run that particular model and you run it and you see you're not getting what you want, you also look at it again and see, am I misspecifying the model? Is it that a particular observed variable is not related to one latent variable, or maybe I don't even need one particular observed variable inside this my model? So these are a list of questions which you look at. And that's why I told you earlier on, inside that diagram I showed, I don't know, is it coming up? Is the diagram coming up?
Not yet.
Not yet.
Okay, I need to share the window. Okay, this is the diagram. Okay. So these are what will allow us to know how important a particular observed variable is. So most of the times you can see an observed variable having a value of 0.03, 0.02. So such observed variables, you try and remove it from the model and you run your analysis again to see how your model fit has already improved. Because sometimes when you remove such observed variables, you can see that your model fit is going to improve. But you can see from this information, most of our observed variables have actually actually related to the level of our latent variables which were measured, such as level industrialization in 1960. You can see we have X2 is having a value of 2.18. So these values allows you to know how important that particular observed variable is in the model.
Sorry, sir. On this, before you move, the values here, are they the estimate?
Yeah, we call them the factor loadings. That is for the observed variables and the latent variables. We call them the factor loadings. Why between the latent variables? Because this one was a regression we specified. These are the coefficient estimates.
Okay, but did we define what the factor loadings are earlier in the slides?
Okay, the factor loadings. The factor loadings actually allows you to know how important the observed variable is to a latent variable. So the higher the value, the more important that particular factor loading is in the model.
So the cutoff point is 0.5.
Yes, for some literatures, but most literatures actually use 0.5. Most literatures use 0.5. Some can actually even go stricter than that and say 0.8 or 0.7.
Okay.
Thank you very much.
Thank you so much, Ridwan. There are some questions here on the chat. So I'll go ahead with Lekpa Ate's question. Does Lavaan already have some models in the library we can use?
No, you have to specify your model yourself. It depends on your data set. So that's one tricky thing about it. Sometimes, in fact, it involves a lot of trial and errors because sometimes you specify a particular model and you get wrong model fits. So you have to look at your values carefully and see what are you going to drop. And is there any covariates which are not actually specifying? So that's why I said, mentioned one of the limitations of the Lavaan, one needs to specify the model correctly. Wrong specification, you have wrong model fits. So it doesn't have any model. You're going to specify those model objects yourself.
Okay, this is an observation, a very important webinar. That's a plus for you, Ridwan. Thank you. So as Gia is saying that, okay, as I use AMOS, there's AMOS for SEM, that's the topic we're dealing with today. So it said, but our software is quite easy. So that's the plus for R and simple as compared to AMOS, okay? Plus point is not needed to draw part in R as was done in AMOS. So I think that is another plus for R. So, so I think that's all for what's on the chat. So if you have any other question, okay, Eric is raising up his hands. You can go ahead.
All right, so thank you very much, sir, for the presentation. When you were talking earlier, you said structural equation modeling has to do with factor analysis and regression. I didn't see you mention path analysis. With that being said, in structural equation modeling, is our aim not to predict, or is predictional part of our model specification?
Okay. Sorry, earlier on, I was actually saying it's an extension of regression and factor analysis, which is more advanced than factor analysis and also regression. So that's what I'm trying to point out.
Yeah. Yes.
So it's just like an extension, which means things they can't cover, SEM model can actually cover such things. So it's just an extension of these particular two techniques.
Okay, and then one more thing. Of late, per my readings, it's like literature is trying to suggest that prediction is not really the case, but rather we should say that these variables explain rather than these variables predict. And I don't know, in your perspective, how you review things. Can we say that these variables predict or these variables explain these kinds of variables?
Yeah, that's what I was explaining earlier on, that this square that you're looking at with this particular are just the relation between latent and observed variables. But what we're actually interested in are these three variables. You can see industrialization in 1960s is predicting this particular one, while industrialization in 1960s is predicting level of democracy in 1965. So this is actually like these three overs you're looking at are like the main or the key information we're interested in. If our variables were actually observed variables, we don't need to be performing SEM analysis. But because we want to know how does level of industrialization in 1960 affects level of democracy in 1965, and also how does level of democracy in 1960 affects level of democracy in 1965. But these variables we want to be using, they're latent variables. We don't have information of them, and they're not something that we can actually have a value or we can actually get values from them. But we already have information on their observed variables. So why don't we use the observed variables to get information for these latent variables? And once we're already able to get those information, we now use these latent variables to predict each other. So this is what SEM analysis is trying to do. So our main question was actually to answer how does level of democracy in 1960 affect level of democracy in 1965, and also how does level of democracy, level of industrialization in 1960 affects level of democracy in 1965. And this is where you now see that we have this particular estimates we have already gotten, just like in your regular regression analysis. You interpret it just like the way you interpret your regular regression analysis. And you can see that also from the results I showed earlier on, all of them were significant.
All right, thank you very much.
You're welcome.
That's my question,
okay,
sir.
We have another question.
Yes.
Okay. Sir. Okay, Umar, you can go ahead. There's another question in the chat. So after Umar, I'll read that out. Thank you.
Okay. First of all, it's a very nice presentation. Thank you for that. My little observation or contribution with that. Can we have another time to have other examples, maybe to touch on some other things to really grab the logic behind or the concept behind the structural equation model more? With this, we are okay, but if we can get another time to have more, it will be better. Secondly, I would like to personally have your number. Maybe probably we'll have to communicate later subsequently, because there's a work I wanted to do or about doing or I'm currently doing on it has something to do with structural equation model, but I have to drop it probably because some of the people therein may not be able to even interpret it. So it will cause some issues. So I decided, but with this, it has myself, I've gotten a little better idea about the whole concept. And lastly, this data you use, I noticed you said it is there in the package. Is it only this one, or there are other data there in the package that we can be able to use and demonstrate and practice?
I don't know for sure. I think there should be more data sets in the package.
Okay.
I think there are more example data sets in the package. So, but this is actually the link to the Lavaan package documentation. So I think I'll be sharing that. Maybe when I'm sharing the slides, you can have access to it. The Lavaan project. So this is the documentation for the particular Lavaan package. So this is the documentation.
Okay.
So this is the documentation for this particular package.
Okay. All right. Thank you.
For other data sets, I don't know for sure. Myself, if I will check, but I think there should be also other data sets which one can also use.
Okay. So, but what about the phone number? Can I get?
Okay, yeah, that's no problem, sir. Maybe.
Thank you.
Yes. Okay, I think you can give him a direct chat on the chat box and share your number there. So let me go ahead with the question.
Umar. Is Umar.
Umar. Okay, so thank you. The question here from Gia is that can we also use our software for EFA, that's explanatory factor analysis, So you're the speaker today, so you have answered that.
Okay, so for the EFA, I don't know. Let me see the lab. I think I saw something like this. Okay, it's actually CFA that is here. So it's actually complementary factor analysis. Oh, well, this I can't say for sure if there's a way to do CFA. I can say the CFA is also. I think I'll need to check on this. I need to check on this. Yes. Okay. I think, is that all for the questions?
Thank you very much, sir.
Thank you very
hello.
much.
Okay.
Okay.
Okay. So Gia, I think we can. So, okay, Eric, I got your number. We'll add you there. I'll share the link with you. Okay. So, do we have any other question? Any other question?
So I wanted to point out that, yeah, could there be a session where we can have some practical experience?
I'll try and work on that for the future.
Yeah. Don't worry.
Was pointed on some. Okay. We can have that practical.
Okay, I think a lot of yearning are there for a practical session. So Ridwan, we have to hold you down. Okay. We need to have another session. Okay. So that's something that we'll have to work on. So we're going to work on that. So don't worry, we're going to work on that. They might be kind of theoretical for now. So but we're going to have another session that is going to come back. So he's part of us and we still have him. So do you have any question, observation? This has been wonderful. Question. Okay. So would you want to round up on the resources that you want to share with us, Ridwan?
Okay, so these are just the resources. Maybe when I'm sharing the PDF for the slide, I think we will have access. I'll share it on the group. So can actually have access to the process. So this is actually the introduction to R for data science, chapter 6 talks about structural equation modeling, and also chapter 6 for using R for social work research also talks about structural modeling. Why the Lavaan project is the documentation for the Lavaan package itself. So though these are just resources, because most of the times not a lot of resources are online for SCM with R, but I think these are sufficient enough and it contains a lot of information which one can dive into. Especially, I know someone of SCM learner for mathematical application, so you can see a lot of information also in these links. So I'll be sharing it. You will be able to access the link by the time when I share the PDF inside the group chat.
Okay. Okay. So, any other question? And this has been really fantastic. Despite the holiday season that we're in. We really appreciate everybody for their presence. It is a large number. We're grateful for your presence here, and it's been very interactive. Well, we're really good at that.
Very much.
Okay, we have
I'm
so
still
many.
waiting for the numbers, sir.
Okay, I've sent it to. Sorry, please. I don't know.
Couldn't see.
Let me see it. I sent it to Umar. Is that not it?
Yes, that is it.
Okay, have you seen it?
Not yet.
Let me send it again.
Okay.
I think you should see it by now.
Okay, I think we're going to round up now. We're not getting any questions. So okay, sorry, Umar, are you on our WhatsApp group?
Yes, I'm there.
Okay, I think you can catch him up there. Well, he's going to check, he's going to link up with you. So he's also on the group. Okay. So we can continue the discussion there. So thank you. I want to use this opportunity to thank Ridwan. This has been a wonderful presentation. I've always appreciate you. You're a good instructor. You're kind of naturally born instructor. So thank you so much. It was a wonderful presentation there. So I believe with all the comments and the one we have in the chat and what everybody has said so far. We're grateful for this wonderful time. So thank you everybody for joining us. And at this point, okay, I believe we're going to share the link. Okay, Florian, let me. Okay, I've shared directly to you. If you're requesting to join the WhatsApp group, I've shared the link with you now. So you can join the WhatsApp group, then we'll continue networking and learning from each other from the group. So thank you, everybody. And thank you so much, Ridwan, for all those who join us from Nigeria and from all around the world. I can see some old faces there. Joshua, thank you so much for joining us. We're grateful for your presence. Thank you so much. So to everybody, it's a wonderful time with you. Thank you and God bless. Bye.
Thank you very much. Thank you very much, everyone.
Bye-bye.
Bye-bye.